Ever wondered how computers handle tricky logic problems where rules can change or contradict each other? Today, we're diving into a fascinating concept called Approximate Fixpoint Theory, a tool that helps us navigate complex systems where traditional logic falls short. Let's break it down step by step, starting with some foundational ideas. Imagine a library where books are organized not just by genre, but by a hierarchy of ideas. Some books are more general, others more specific. This is similar to a partially ordered set, a mathematical structure where elements can be compared in certain ways. For example, if we say novels are a type of book, we're creating a partial order between these categories. Now, think of a group of books in this library. An upper bound would be a book that's more general than all of them, while a lower bound is more specific. The least upper bound is the most specific book that still includes all others, like a supercategory that ties them together. Similarly, the greatest lower bound is the most specific shared theme among them. But here's the catch. Not every group of books has a clear upper or lower bound. Sometimes the hierarchy gets too tangled. This is where chains and anti-chains come in. A chain is a sequence where every book can be compared, like a timeline of ideas. An anti-chain is a group where no two books are directly related, like a collection of unrelated topics. Now let's talk about fixpoints, a concept central to this theory. Imagine a machine that takes an idea and transforms it. A fixpoint is when the input and output are the same. The machine doesn't change the idea. For example, if you feed a circle into a shape-rotating machine, and it spits out the same circle, that's a fixpoint. But what if the machine isn't straightforward? This is where monotone induction comes in. Think of it as a step-by-step process where each step builds on the last, getting closer to a stable answer. The Naster-Tarski theorem tells us that if our machine follows certain rules, it's monotone. There's always a least fixpoint, the simplest, most consistent solution. But here's the twist. Real-world systems aren't always so tidy. What if new information changes everything? That's where non-monotonic reasoning steps in. It's like solving a puzzle where new pieces keep appearing, and your answer has to adapt. This is where approximation fixpoint theory, AFT, shines. AFT helps us find stable solutions even when rules shift. Think of it as a detective searching for clues. Traditional AFT used intervals, rough estimates, like saying a number is between 5 and 10. But intervals are like a compass, useful but missing the details. Take an auto-epistemic agent, a self-aware robot reasoning about what it knows. Suppose it evaluates a statement. If I don't know P, then Q is true. Intervals can't capture how the robot's beliefs evolve. It's like trying to map a city with only a compass, useful but missing the streets. Another example, weighted abstract dialectical frameworks, WADFs, which model arguments with confidence levels. Imagine a paper review system where each argument has a confidence score. Traditional AFT struggles because there's no clear top confidence level. Without that, intervals fail to represent the full picture. So how did researchers fix this? They introduced refined approximation spaces. Think of them as a more precise map for navigating complex systems. This allows us to handle dynamic rules without losing track of stability. But here's a critical insight. More precise tools don't automatically mean better results. Think of it like a camera. Imagine you've got a super high-tech camera that captures every detail, but your phone's photo app can't handle the data. The result? A mess. The same logic applies to complex systems in science and tech. The study introduces the idea of an ultimate approximator, like a cheat code for solving problems. It's not about having the most precise framework, but pairing it with the right software to make sense of it. However, precision often comes with a cost. A more detailed framework is like upgrading from a basic calculator to a supercomputer, powerful but slower and resource-heavy. The secret sauce? Iterative refinement. Like tuning a car engine, adjusting parts step by step to find the sweet spot between speed, power, and efficiency. The takeaway? Balance matters. Precision is important, but it's how you adapt and refine your methods that unlocks success. Next time you're tackling a problem, ask yourself, am I using the right tools for the job, or am I just chasing the flashiest options?